とはい、それでは始めます。今日はっていうか、私は、ツイッターで古賀先生です。それで、最近のツイートで、これね、SusskindQM、ハッシュタグSusskindQMで出てきます。それで、コンパスでアナウンスしてます。で、今日が第9回目じゃないか。ブルーキャットでもアナウンスをしてます。第9回目で第9章のパート5、301ページからやります。それで、本はここにあるレオナルド・サスキンドのクオンタム・メカニクスです。それで、テキストはここにあります。ここにあるので、ここからダウンロードできます。それでリツイートいただいたのかな。リツイートいただきました。それからあれですね。実は予定が出てくる。これで配信。ここに出てきた。次回が今日が、今、この日曜日の10時からの枠でやってます。で、次回が 今晩の9時からやります。それでちょっとこれ自分では答えられないんだけれども、明日は、3月7日マンデーは11時のブルーキャット枠があるので、ここで、開催したいと思います。3月7日に、月曜日11時に、港社長にアナウンスをお願いしているところですが、そのうちアナウンスがあると思います。どういうことかというと、コンパスを見ればいいのか。コンパスを見て、ダッシュボードに行く。それで、ここにこういう風になってて、この7日の、今日もブルーキャットがあるね。7日の、11時の枠が空いてるので、私のために開けていただいているので、この7日の11時のブルーキャット枠で開催をしたいと思います。こうやって、今日これがありますよね。3月6日。これ、丸つけてんのな。なんで丸つけてるのにダメなんだろう。ブックマークをして、これ消えないのか。出てるか。ここに出てます。11時から。すいません。余計なことはいいとして。じゃあ301ページからね。今日は301ページからです。で、この回転を合わせて、こうやって、だいたい39ページぐらいかな。301ページ。まだ。経路積分からね。なかなかいい感じじゃないでしょうか。パスインテグラルということで、経路積分。Classical Hamiltonian mechanics focuses on the step-by-step incremental changes in the state of a system. But there is another way to formulate mechanics, the principle of least action, in which the focus is on entire histories. そうですね。ちょっと、実はですね、ちょっと待ってよ。この YouTube、これか。これ、is on entire histories。一人しか視聴してないの。これでじゃあ entire histories。For particle, this means 最小作用の原理ですね。Principle of least action. For particle, this means looking at the full trajectory of the particle from some initial time to some final time. The content of the two approaches is the same, but the emphasis is different. Hamiltonian mechanics zeroes in on some instant and tells you how the system changes between that instant and the next. ハミルトニアンメカニクスゼロスインってなんだ？誤色？ 誤植でしょうかね。照準を合わせる。照準を合わせるです。ゼロインオン。ゼロインオン。照準。照準。照準。Hamilton mechanics zeros in on some instant and tells you how the system changes between that instant and the next. The least action principle steps back and takes a global look. One can imagine nature sampling all possible trajectories and picking the one that minimizes the action between a pair of fixed initial and final points. Footnote 7. Strictly speaking, the principle should be called principle of stationary action. Actual trajectory as stationary points of the action are not always minima. For our purposes, this fine point is not important. Anyway, quantum mechanics also has a Hamiltonian description that concentrates on incremental changes. It's called the time-dependent Schrödinger equation, and it's very general. As far as we know, it can be used to describe all physical systems. As far as we know, it can be used to describe all physical systems. Still, it seems fair to ask, as Richard Feynman did almost 70 years ago, whether there is a way to look at quantum mechanics that pictures whole histories. In other words, is there a formulation that parallels the principle of least action? I will not explain Feynman's path integral description in detail in this lecture, but just to whet your appetite. 難しい単語が出てきた。whet。ホイット。なんて読んだのこれ。ホイット。読み方が書いてない。Hoit your appetite. I will give you just to hoit your appetite. I will give you a hint of how it works. First, let me very briefly remind you of the classical least action principle as I explained it in volume 1. Suppose that a classical particle starts at position x1 at time t1 and arrives at position x2 at time t2. Let's look at figure 9.5. The question is, what is the trajectory that it took between t1 and t2? According to the least action principle, the actual trajectory is the one of minimum action. Action is of course a technical term, and it stands for the integral of the Lagrangian between the endpoints of the trajectory. Integral of the Lagrangian with respect to time. With respect to time, or by time. Integral of Lagrangian integration. You can also say integration. Integration of the Lagrangian by time between the endpoints of the trajectory. For simple systems, this is the trajectory between T1 and T2. The position become x1 to x2. Classical trajectory. This shows one path a particle may take when moving from point 1, x1 t1, to point 2, x2 t2. To keep things simple, the x-dot axis representing the particle's velocity in the x direction is not shown. The Lagrangian, let me see, what was that? For simple systems, the Lagrangian is the kinetic energy minus the potential energy. Thus, for a particle that moves in one dimension, the action is so. Here, Lagrangian is kinetic energy minus potential energy, and this is a function of x and x dot. Then this is action, and this is Lagrangian. And action is the time integral of Lagrangian, or integration of Lagrangian by time from T1 to T2. That's the action. There is a figure 9.6. First step toward quantizing the trajectory. Break the particle's path into two equal parts, equal in time, that is, the particle has the same starting and ending points, but now its trajectory passes through the intermediate point x. So here, action. This is the Lagrangian. This is the T. This is kinetic energy minus potential energy. So this is Lagrangian. And this is action. Action, and here is Lagrangian. Okay. The idea is to try out all possible trajectories connecting the two endpoints and calculate A for each one of them. なんだこれ。This is the figure 9.7. Further steps toward constructing the path integral, keeping the same starting and ending points, break the path up into a large number of equally sized segments. なんだこれ。The winner is the one that has the least action. Okay, so this means you calculate action. See, if you give one pass, this is one pass. Another pass, like 2 pass, 3 pass, 4 pass. Okay, so each pass you can calculate action. So for one, this is if you choose pass 1, you obtain action 1. If you choose pass 2, you obtain action 2. If you choose pass 3, you have action 3. If you choose pass 4, you have action 4. So you have infinite number of actions. A1, A2, A3, A infinity. You have infinite number of actions, and whatever, for example, if there is some special action, for example, this, let's see, this is I, anyway. So then if AI is smallest, if this is smaller than A1, A2, A3, AI minus 1, AI plus 1, So if this AI is the smallest, this is the trajectory. So this AI is the smallest. This AI is the smallest. Then trajectory I is the trajectory that is realized. Okay. Other trajectory will not be realized. For example, see, this AI can be parabolic. See, you can say, so this is the X, and this is Z, and there is a gravitational force. So if you throw a ball, you have parabolic path. Yeah? This is AI. And if you can also imagine other paths looks like this. Strange this way. This is the action of this is this side. So the action of this realized path is this one, the minimum value. So this is the way to think using stationary action principle. So you consider all paths. So, and the path which is realized is called winner here. Here it's called winner. Winner is the one that has the least action. Let's skip the footnotes. Now let's turn to quantum mechanics. The idea of a well-defined trajectory between 2 points makes no sense in quantum mechanics because of uncertainty principle. Anyway, however, a question that can ask is, given that a particle starts out at x1 t1, what is the probability that it will show up at x2 t2 if an observation of its position is made? This is very strange. The idea of well-defined trajectory between 2 points makes no sense. Okay. Well-defined trajectory between 2 points makes no sense in quantum mechanics because of the uncertainty principle, but it seems like it is saying it makes sense to assume well-defined starting point and well-defined ending point, because it says I'm not so sure. This is very much well-defined starting point, and this is very much well-defined ending point, and I don't know why he doesn't apply uncertainty principle to these endpoints. But he says he apply uncertainty principle in the trajectory. Anyway, what is the probability that it show up at, given that particle starts out at x1 t1, what is the probability that it will show up at x2 t2 if an observation of its position is made? Okay, so this one actually you can say this is a probability density. Yeah, then you can make observation of only its position. Then, okay, uncertain. There is no uncertain. If you can make position measurement as accurate as possible, then you can talk about probability density. As always in quantum mechanics, the probability is the square of the absolute value of a complex amplitude. The global version of quantum mechanics asks, given that a particle starts out at x1 t1, what is the amplitude that it will show up at x2 t2? So everything you can just add density, probability density, and this amplitude is also a kind of amplitude density. Let's call the amplitude C, x1 t1, x2 t2. Let's call that amplitude C, or more simply just C12. Let's call that amplitude C x1 x2, x1 t1, x2 t2, or more simply that C12. The initial state of the particle is psi t1 equal x1. Over the time interval between t1 and t2, the state evolves to psi of t2, which is exponential minus ih t1 minus t2 minus t1 times state x1. The amplitude to detect the particle at x2 is just the inner product of psi 2 with x2. Its value is c12 is x2 ket x bra x2 exponential minus ih t2 minus t1 ket x1. In other words, the amplitude to go from x1 to x2 over the time interval t1 minus t2, t2 minus t1 is constructed by sandwiching exponential minus ih t2 minus t1 between the initial and final positions. To simplify the formula, let's define t2 minus t1 to be t. Then the amplitude is c12 equal x2 exponential minus iht x1. Now, let's break the time interval t into two smaller intervals of size t over 2. Please see figure 9.6. The operator exponential minus iht can be written as the product of two operators, exponential iht minus iht equal exponential minus iht divided by 2 times exponential minus iht divided by 2. By inserting the identity operator in the form. This is important. I think we did it a little bit before. This is identity operator. We insert this identity operator in between here. We insert identity operator between exponentials. We can rewrite the amplitude as this. This form of the equation looks more complicated but has a very interesting interpretation. Let me put it in words. The amplitude to get from x1 to x2 over time interval t is an integral over an intermediate position x. The integrand is the amplitude to go from x1 to x over the time interval t over 2 multiplied by the amplitude to go from x to x2 over another time interval t over 2. Figure 9.6 shows the same idea in visual terms.これ 9.6 okay. Figure 9.6 shows the same idea in visual terms. Classically, to go from x1 to x2, the particle must pass through an intermediate point x. But in quantum mechanics, the amplitude to go from x1 to x2 is the integral over all possible intermediate points. Yeah, okay, so you can say classical path. This is the classical. So it will go through these points. Particle goes through this point. Quantum mechanics. Amplitude is integration with x. So here x. So there is all path. So this quantum mechanics particle go through all points. Because you have integration of something. So quantum mechanical probability amplitude is given by the integration of all possible points. But in classical particle, go through only one point at time, t over 2. Time t over 2, classical particle goes through only one point, but quantum mechanical particle go through all points because you have this is the integration of all points. Here is a time t over 2. From figure 9.6 shows the same idea in visual terms. Okay, we did it. We can carry this idea further and divide the time interval into a great many tiny intervals as illustrated in figure 9.7. I won't write out the complicated formulas, but the idea should be clear. For each tiny time interval, say of size epsilon, we include a factor, then between each pair of factors, we insert the identity so that the amplitude C12 becomes a multiple integral over all the intermediate locations. the integrand is built from products of expressions with the form. If we define u of epsilon to be like this, then we can write entire product as this or this way. In this equation, u appears n times as a factor where n is the number of epsilon steps. We can then insert identity operators between the u's. Such an expression can be called the amplitude for the given path. But the particle does not travel along a particular path. Instead, in the limit of a large number of infinitesimal time intervals, the amplitude is integral over all possible paths between the endpoints. The elegant fact that Feynman discovered is that the amplitude for each path bears a simple relation to a familiar expression from classical mechanics. The action for that path, the exact expression for each path, is exponential IA h bar, where A is the action for the individual path. Feynman's formulation can be summarized by a single equation, C of 1, 2 equal integration over all paths exponential IA divided by h bar. The path integral formulation is not merely an elegant mathematical trick. It has real power. In fact, it can be used to derive both Schrödinger equations and all the commutation relations of quantum mechanics. But it really comes into its own in the context of quantum field theory, where it is the principal tool for formulating the laws of elementary particle physics. So we can stop here. And what is this? 311. 311. Nine. I think I can explain this path integral a little bit more next time. So let's see. I can explain path integral a little bit more. But it's night. So so this one, it's okay. and this one. Let me see. なんだっけ。編集。21。OK。3月6日21時から21時40分、311ページから、第10回10章パート5ね。それでコンパス。コンパスも、編集で、これが21時か。それで、10章パート1、311。あれ10章入らないのか。こうするか。それで10章パート1章、これ合ってるっけ。間違ってる。10章パート1で、それからなんか直そうと思ったんだけど、10章パート1でしょ。いいのか。いいよね。これで OK で、とりあえず終了します。そうか。それでSusskindQM をやって、次回は3でこう大丈夫ですね。3で21時、マンデーを教えていただいた人がいるので、次回は今晩9時、その次は、月曜日の11時ということでやりたいと思います。じゃあ終了します。